Palladium Minds, a podcast about scientific developments and how they move from the laboratory scale up to the real world application. For instance, in the case of Professor Li, we had methane and carbon dioxide, which are two quite problematic greenhouse gases, and because they are both in the highest oxidation state, so it's quite difficult to work with those two molecules. And even more surprisingly, Professor Li was able to use them both at the same time. Of course, there's a lot of chemistry behind that, and it's not only an issue for chemistry, it also affects how we use our carbon in the real world, because carbon dioxide and methane both are C1 sources. So the question is, can we turn those two difficult problems into one practical solution? I'm Professor Francis Verpoort. I'm the chair of the International Expert Council of the Palladium Global Science Award. Very honored to have the guest, Professor C.G. Li, and I thank him for joining us and finding some time to have a talk about his real interesting research work.
Thanks, Francis. First of all, it's really my great pleasure to be here today.
CO2 and methane are usually treated separately. There are techniques and applications for carbon dioxide itself. There are techniques and applications for methane itself. But the combination of that is actually very unique. And you bring those two together in one system. Why has this been so difficult to achieve?
Both methane and the carbon dioxide are very stable molecules, and the bond are very strong. And traditionally, in order to activate them, to make them to react, you need to heat it up to very high temperature. That's one of the reasons for a long time of people trying to either to activate one or the other, because trying to activate both of them at the same time is very, very challenging. So you need in order to activate the methane, you need an oxidizing reagent to help the activation. And in order to activate carbon dioxide, you need a reducing reagent to help the activation as well, of course. However, because both of them are so unreactive, you need very high temperature. And so in the end, the only product they can produce is through what they call the dry reforming, to generate the syngas. You cannot generate something else useful. In order to activate either methane or CO2, you need to reach to a very high temperature. And furthermore, if you want to activate them simultaneously and to convert into something useful, it's also even more challenging. So I've been trying to do it through what they call the dry reforming. But in that case, we only produce syngas, which is carbon monoxide and hydrogen gas, because that's the only main product you can produce, but you cannot produce complex molecules directly.
Just for the audience, syngas is a mixture of hydrogen and carbon monoxide, and it's a very useful mixture actually, because you can make all kinds of aliphatic compounds, even gasoline and so on. You can make this with your syngas. Okay, so it's not just one problem, it's two challenges that you combine at the same time. So what made you think it might be possible to work with both gases in one system? Why you thought about that? Because it's not straightforward, right?
Indeed. Even though it's a challenge, but we were thinking about this from three different aspects. First of all, we thought if you balance the equation, if you just move the oxygen from the carbon dioxide into methane, in principle, you can get it. Of course, that's on paper, right? In our lab, we're able to independently to activate the methane at room temperature with light, and also we're able to activate carbon dioxide with light at room temperature. So therefore, in principle, we propose that potentially we can bring them together to react. Of course, even though it's a very small amount, but it's very encouraging. Then what we need to do is to try to find a way to optimize the condition so that we can generate this with a very high efficiency and selectivity.
So you are combining two very stable molecules and doing it under relatively mild conditions, right?
It's a room temperature with light. And in fact, if you calculate the thermodynamics of reaction, we need to have energy input. However, with the light, it provides serve two rules. First of all, it gives the input of the energy needed for the thermodynamics. Secondly, the light activates the catalyst so that at room temperature, you have a highly reactive catalyst, and now you can break both very stable bonds. So, as I mentioned before, for the methane, in order to activate, you need an oxidizing reagent. For carbon dioxide, you need a reducing reagent to create a what you call the electron hole and also create the electron. So the electron is the reducing reagent. The electron hole is the oxidizing reagent. So the oxidizing reagent will oxidize the methane, and the electron hole will reduce carbon dioxide at the same time. So it really produce the highly active catalyst to activate both at the same time.
So how did you manage to keep them away from each other?
So that's where palladium comes in. So palladium plays several very important roles. One is you need something to separate the electron and electron hole. Secondly, you need to activate both molecules, and you also need to bring these two molecules together in order to react. Bring the intermediate together in order to react. So in the end, you can have a highly selective reaction. So actually, palladium has several roles. Palladium can actually help to separate the charge, the electrons and electron holes that can separate the charge. Secondly, palladium can activate the methane molecule in basically to generate spill species. But furthermore, palladium is very good to stabilize the intermediate so that they have enough time to react with the other intermediate from the carbon dioxide.
So palladium
Yeah.
is a very helpful metal then. It's key for your catalyst actually, right?
Right. So yeah, without these at the beginning, as I mentioned at the beginning, we were able to observe very small amount. But the question, how to increase the efficiency, you need to have all these things. So the trick is by using the small amount of gold and small amount of palladium, and now you can essentially help all these three aspects so that you have very highly selective process.
So without palladium, your system would not work in the same way. If you would remove palladium and you only have gold on your semiconductor, this still does something, or you have a total different reaction, or maybe nothing. I don't know.
You have a trace amount of product, but it's also a mixture of other things as well. Well, it has a very low efficiency in terms of how to essentially transfer oxygen from carbon dioxide into methane to produce methanol.
So before we move on, if you want to understand how complex chemical ideas turn into real technologies, follow Palladium Minds. Each episode breaks down one development and how it can actually be used. So many promising reactions remain at the lab stage, and your work is recognized as a development. How close is this system to the real world applications? As I mentioned, plenty of reactions are made in the lab but never reach society. So in your case, what's your situation? You already in moving to the real world applications, or we are somewhere in between, or still in the lab?
Most of the chemical technology, in order to go from lab scale to industrial, usually takes about 10 years, right? That's a normal development. And like you mentioned, most of them will not go to the practical application. And actually, traditionally, in order to convert them, it's very difficult because you have to separate them into pure either the methane and CO2. That separation is very challenging, but also very costly. These mixtures very expensive. So therefore, it's conditioned much closer to the real world. The work has been licensed to a startup from McGill, and they are turning this into a flow system. And so with the proof of concept is working in a very small flow system. So there's good promise at this stage. So the work was initially developed on the lab scale, but it's different from the other lab scale experiment, because most of the lab scale experiment you use either pure pure methane or pure carbon dioxide, and etc. But in the real world, most of the methane, carbon dioxide coexisting, such as from the biogas, from the landfill runoffs, from the flare gas in the petroleum industry, etc., or from shale gas. But all work, in fact, use the mixture, which is almost the same. So you can literally use the practical the mixture from those sources and then convert them. This work has been licensed into a spin-off company from McGill, where we tried the proof concept or the first testing on a flow system. Because in order to use it, you have to go to, in the industrial practice application, you need to go to a flow system. In a lab scale flow system, is already working. So essentially, there's a promise where we can basically bring this into practical world applications.
What would stop this from being used in the practice? Is it something that could say, if you don't have a certain yield or something like that, or selectivity, then that would be a no-go for industry?
The biggest challenge for this technology, but also probably for most of technology, how to transfer the really very small lab scale to the industrial scale without affecting the efficiency and selectivity and the production rate, right? So it's a huge challenge, but there are very few photocatalytic processes being commercialized. So we have to find the ways to probably more creative ways to bring this into an industrial scale. The biggest barrier is how can we essentially turn the very small scale into a flow system where you can go to a large scale but keep the same efficiency, the selectivity, get the same kind of selective formation of the desired product without generating the byproduct, which is could be very different from the lab scale. And also, ideally, at this stage, we need to use a light, which of course, the light is being generated from electricity, right? So ideally, if we really want to make it even better, it would be nicer to use the sunlight directly. So the sunlight plus the photo energy. So the sunlight would be ideal, and then we're still thinking about how to turn this process into a sunlight-driven process.
So we know that you produce methanol and CO, right, from your system. So how such systems can be used in practice? So which industries you are targeting, or which industries would benefit most from your system? So your system, can it easily be integrated in the existing industry?
In many cases, they are wasted and released to the environment. Potentially, you can use like a small scale, small reactors, and then converting them into the product. The nice thing about the product is it's separate by themselves. You have liquid methanol. As I mentioned, it's a very important fuel, but also a very important commodity chemical. At the same time, you have a carbon monoxide. Carbon monoxide potentially, and then we can use it like a syngas, use it for other applications, or even capture, because the reaction produces gas and liquid are separate by themselves. So that's really one nice thing about it. Collect some of the real world mixture and then trying to test it and see whether how long it can go without the, for example, the deactivation of the catalyst. The petroleum industry, for they burn their flue gas because the mixture of carbon dioxide and then the methane, and it's not very useful to just burn them. And the other thing, so these completely wasted, but plus it release to the environment. So potentially we can, if the reactors working in a flow system, we can directly apply there. And the other industry is actually the carbon capture, storage, and utilization process, because they already have a lot of carbon dioxide and then methane probably present, and we can use them. Or the other potential process like the landfill and the biogas, like from the biogas from the agriculture industry and then from waste. So potentially you can again turn the dilute mixture into like useful product. Yeah, because in most of the in the existing industry, most of the time these mixtures are waste, right? Like a plug in into the collected waste and directly converting them into flow. It's like turning on the tap of water. So basically, it's constantly turning the waste gas into the methanol and the CO. So if, for example, the catalyst can survive the conditions, so in principle, you can directly plug in to their waste stream.
I know behind every development there's a long and uncertain research process. And from my experience, I also developed some catalyst, and sometimes it's sweat and tears and blood all together, a lot of efforts, and then sometimes nothing happens anymore, or something is very exciting. So, what about you? Where was there a point when you thought, this doesn't work at all?
For this particular process, even though at the beginning we observe a trace amount of methanol, which is what we really want, but of course the major product, all the different kind of mixture byproduct, many different conditions trying to tune the catalyst, but we're never able to increase the efficiency. But we're never able to get a very high efficiency and a high selectivity to the metal. So until our student putting them both together, suddenly you get extremely high efficiency and selectivity to the methanol product.
What was the main significance of this development?
Yeah, so really the main significance of this work is that it introduced a new way to convert the two of the most abundant greenhouse gases, the two bad gases, which is carbon dioxide and methane, where we all worry about, together to produce highly valuable and a very easily separable methanol and the carbon monoxide for the first time, and at a very mild conditions as well. So this really represents not only a new reaction pathway, but also a novel mechanism that can challenge how molecules are traditionally treated.
So the principle is to think out of the box. That's what you did, right?
Right, exactly. Yeah.
It's about turning a difficult chemical problem into something that can be actually be used. I think this has been Palladium Minds. It's a podcast about scientific developments becoming real technologies. And today we talked about how two difficult molecules, carbon dioxide and methane, can become a very useful resources. Follow us on our website, YouTube, LinkedIn, and WeChat to stay updated. And if you are developing technologies with Palladium, consider applying to the Palladium Global Science Award.